All right, let's dive in. Today, we're going to pull back the curtain on the invisible connections that literally run our world. We're going on a journey that starts with the headphones you might be wearing right now and scales all the way up to the entire globe. Let's get started. I mean, have you ever really stopped to think about it? It's one of those things that's just magic, right? It just works. Well, in the next few minutes, we're going to demystify that magic and break down exactly how it all fits together, piece by piece.
You know, to really get our heads around the big picture, we've got to start small. So we're going to begin with the network that exists just a few feet around you, and then we're going to zoom out step by step until we're looking at the whole planet.
Okay, so this table right here, this is basically our roadmap for the first part of this journey. We've got four main types of networks, and the only real difference between them is size, the area they cover. You've got PAN, LAN, MAN, and WAN. Let's figure out what all those letters actually mean.
First up, we have the PAN, the Personal Area Network. Seriously, think of it as your own personal tech bubble. Connecting your phone to your Bluetooth headphones, that's a PAN. Your smartwatch syncing with your phone, PAN. It's tiny, it's all about you and your gadgets. Now let's zoom out a little bit to the LAN, the Local Area Network. This covers a bigger space, like a single building. Your home Wi-Fi network that connects your laptop, your TV, your phone, that's a perfect example of a LAN. Or think about all the computers in a school library or your office. They're all on a LAN together.
Okay, zooming out even further, we hit the MAN, or Metropolitan Area Network. Now we're talking big, a network that can cover an entire city or a huge university campus. The classic example? Your city's cable TV network. That's one giant MAN connecting thousands and thousands of homes.
And finally, we get to the big one, the WAN, the Wide Area Network. This is the granddaddy of them all. A WAN spans enormous areas. We're talking countries, continents, the entire globe. And the single best, most mind-blowing example of a WAN, the Internet itself. It's the ultimate network of networks.
So we've got the different sizes of networks down, from personal to planetary. But how are the devices inside those networks actually laid out? How are they physically connected? This layout is called a topology, and it's basically the network's blueprint.
First up is the simplest of them all, the bus topology. Just imagine one long cable, the backbone, and all the computers just plug right into it. Super cheap, super easy to set up, but, and it's a big but, it has a massive weakness. If that main cable breaks anywhere, the whole network goes down. Game over.
Now this one, the Star Topology, is probably what you have at home. All your devices connect to one central box, like your Wi-Fi router. The great thing about this is, if your laptop's connection goes down, your smart TV and phone are totally fine. But it has its own Achilles heel. If that central box dies, the whole network is dead in the water.
Next up is the ring topology, and it's exactly what it sounds like. All the devices are connected in a circle, and data goes around in one direction, from one to the next to the next. It's very orderly, but you can probably see the problem, right? Just like the bus, its biggest strength is also its biggest weakness. If there's a single break anywhere in that ring, the circle is broken and the whole thing stops working.
And finally, we have the Fort Knox of network layouts, the mesh topology. In a full mesh network, every single device is connected directly to every other device. There is no single point of failure. If one connection breaks, data just finds another way to get there. It's incredibly reliable, which is why it's used for supercritical systems like the backbone of the internet and military communications. The downside? As you can imagine, it's crazy expensive and complicated to set up all those connections.
We've talked scale, we've talked layouts. Now let's get into the actual physical gear. The little boxes with the blinking lights that make all this magic happen. People get these confused all the time, so let's clear it all up right now. So let's start with the two most famous boxes in your house, the modem and the router. Here's the difference. The modem is your on-ramp to the internet. Its job is to talk to your internet provider and bring that connection into your home. The router, on the other hand, is the traffic cop inside your house. It creates your local Wi-Fi network and makes sure the Netflix stream goes to your TV and your work emails go to your laptop. One gets you online, the other directs the traffic.
Now for hubs versus switches. A hub is, well, it's dumb. When it gets data, it's like someone standing in a crowded room and just screaming that information out to everyone, hoping the right person hears it. It's noisy, it's slow, it's inefficient. A switch, however, is smart. It knows exactly where the data is supposed to go. It's like whispering the message directly and privately to the intended person.
Way faster, way more efficient, and way more secure.
All right, we have the layout, we have the hardware, but how does the data itself actually talk? How does it move across the wires and through the air? Well, it turns out there are three basic modes of communication. Think of them as the rules of conversation.
First, you've got simplex. This is a one-way street. Information only flows in one direction, period. The best example is broadcast TV or radio. You can listen to the radio all day, but you can't talk back to the DJ through your car stereo, right? That's simplex, one way only.
Next is half duplex. Now, communication can go both ways, and this is the key, not at the same time. Think of a walkie-talkie. I talk, then I have to say over, and only then can you talk back. We can't both talk at once, one at a time. And finally, we have full duplex, which is what we're all used to in our daily lives. This is a two-way conversation that happens at the same time. It's just a normal phone call. You can talk, the other person can talk, you can interrupt each other. It all just works simultaneously.
So for any of this to work, for data to get from one place to another, every single device on a network needs a unique identity. It needs a name, an address. It's kind of like a digital ID card. And every device actually has two of them, an IP address and a MAC address.
So what's the difference? It's pretty simple. A MAC address is like your device's fingerprint. It's a permanent serial number that's burned into the hardware at the factory. It never ever changes. An IP address, on the other hand, is like your home address. It tells the network where you are right now. When you take your laptop from your house to a coffee shop, your MAC address, the fingerprint, stays the same, but you get a brand new IP address from the coffee shop's network.
Now, speaking of IP addresses, you've probably heard of IPv4 and IPv6. This chart shows you exactly why we had to make a change. The old system, IPv4, had about 4 billion unique addresses. That sounds like a lot, but with billions of people with phones, laptops, smartwatches, and even smart fridges, we literally ran out. So along comes IPv6. It creates a number of new addresses that is so ridiculously massive, it's hard to even describe. We are not going to run out of these anytime soon.
And there you have it. So here's a little mission for you. Grab your phone or computer, dive into the Wi-Fi settings and see if you can find them. Look for your IP address, it'll be a string of numbers, and your MAC address. Sometimes they call it the physical address or Wi-Fi address. They're in there. Go find them.
It's kind of wild when you stop and think about it. From your personal little Bluetooth bubble to the entire global internet, our whole modern world is woven together by this invisible web of connections. It all just works, which makes you wonder what happens when a single thread in that web snaps.